All right, hello everyone. It's funny, someone was just in my meeting room. So today, it's pretty late, but I'll be recording the solutions to the final set of homework problems. As a reminder, there isn't class anymore for now. I'll try to get an announcement sometime in the upcoming weeks about when, if there is a fall session. But yeah, let's get right into it. I apologize if this isn't the smoothest recording in advance. All right, just give me 1 second. I need to close the door. All right, so let's get right into it. So the first problem we have is how many numbers that are less than or equal to 50 or less than 50 are not divisible by either 3 or 5. At first glance, this might seem easy to count, but no, not really, since you have to consider both the 3 and the 5 in our calculation. That'll lead to some messy modular arithmetic. Although it's not that messy, but 50 isn't the ideal number. You can work it out that way if you want to. But anyways, the better way is to count the complement, the number of numbers that are divisible by 3 or 5. Numbers divisible by 3 or 5. All right, so now how do we count that? Well, how many numbers are there that are divisible by 3? This is just the floor of 50 over 3. Floor just meaning like the smallest, the biggest integer less than, not the smallest, sorry. And that's obviously equal to 16 because 48 is the biggest multiple of 3, less than 8, less than 50. What am I saying? All right, and so similarly with 5, well, we know this is pretty easy. How many positive multiples of 5 are there less than 50? Or actually, yeah, this should be actually 49 over 3 technically. Because we want numbers less than 50. So but for 5, okay, so we want the same thing for 49 slash 5. That would be equal to, sorry, 9, since 45 is the biggest multiple less than 50. But we want to, this overcounts the numbers divisible by both 3 and 5. Now, how many of those are there? Well, 49 over 15, which would be equal to 3. So our total count would be 16 plus 9 minus 3. Since in the counting 16 and 9, we overcount each one of these multiples of 15 twice. And thus, our answer is 22. Well, and thus our answer for this is 22. So thus, the final answer is 49 minus 22 is equal to 27. Yeah, I almost tripped up there and saying that 22 is the final answer. But no, yeah, must account for that. That is counted the complement. So yeah, be careful. Anyways, the answer is 22. I mean, no, not 22, 27. Sorry, I've circled it in green. On to the next problem. Okay. So our next problem is an octahedral die with the sides numbers 1 to 8 is rolled twice and the product of rolls are computed. How many possible pairs of 2 such rolls produce a composite product? And order of the numbers does matter. Okay. So I did again, we covered complementary counting this week, so we should use that. Well, what's the complement? The complement is that the product is a prime. Or it's 1, because I would not say 1 is composite, although we'll check that later. We can check that always. Okay, so how do we count the number of prime rows you can get? Okay, so order matters. So first of all, how many primes are there? There's 2, 3, 5, and 7, right? and then we pair all of any of these with the 1. So we have 4 options times 2 because it can be either of the die rolls of prime, which is 8. And then 1 times 1 is 1 combination of 1 plus 8 is equal to 9. Right? Okay, so that's the complement. And going back to the original question, well, there are 8 times 8 equals 64 ways to get some pair outcomes on 8-sided die. So our answer is just 64 minus 9 is equal to 55. All right. So that is our answer for problem number 22. I mean, 2 is 55. All right. On to the next problem. You have $10 to spend. At the store, there are 3 types of snacks, costing $1. If you have to spend all your money, how many ways are there to buy snacks? Clarification, the 3 types of candies are A, B, and C. Then, for example, buying 3 of A, 4 of B, and 3 of C is different from buying 3 of A, 3 of B, and 4 of C. To clarify what I mean further, what I mean is like, so we have like A plus B plus C is equal to 10. And in this case, 3 plus 3 plus 4 is not the same as 3 plus 4 plus 3. That is what I want to get across here. And I hope everybody understands that. Okay, so this is just stars and basic stars and bars. We covered this in class. All right. So what do we have? We have 3 variables and their sum is 10. Okay, but we don't have to buy like all of each snack. All right. Like we can buy 5 of A, 5 of B, and 0 of C. Or we can buy 10 of all of one snack. Like what I mean is, we just have to spend a total of $10 on some like group of snacks. We don't have to be diverse, include every single one. Given that, all right, then we add 3 to make it so that it's a sum of 3 positive numbers, just like we covered in class, this like trick or manipulation. It'll show up a lot more in later contests. So we get 13, all right? And now, if you remember, we can just apply the original stars and bars formula from here to get an answer of 13 minus 1, choose 3 minus 1. This is because there are 3 variables. And you can see why is choose the number of variables minus 1 in the derivation for stars and bars, giving us an answer of 66. So it's just 12 choose 2, which is 12 times 11 over 2, 6 times 11, 66 as our final answer. All right. Yep. And if you want to go over the stars and bars derivation again, I'll just go over it quickly here. It's just like if you have a number of stars, let's say you have 4 stars. All right, this is equivalent like to the sum is 4 of some variables is 4, and let's say you have 3 variables. Oh, okay. In each of these gaps between the stars, you can put bars in to like, and what that does is, let's say you put a bar here and a bar here, right? Then that gives 2 stars to the first, that creates 3 piles. That gives 2 stars to the first pile, 1 to the second, 1 to the third as shown. All right. And yeah, honestly, that's just basically how it is. And the number of ways to do this is 3 choose 2 because there are 3 gaps like I shown here, and you're choosing 2 of them since the numbers are all positive. If the numbers are non-negative, I want to emphasize that that does not mean you just add on these 2 gaps here and do 5 choose 2. That is absolutely not the right way. Why? Because, well, like you can have multiple variables be 0, so you can just have like 2 bars like with nothing in between them. And yeah, that causes problems. There's no clean way to count that without making this manipulation. All right. So yeah, I want to make that clear. Anyways, that's all for this problem. That was just a little extra. And on to the last problem. So a standard 8-sided die is rolled 4 times. How many ways can you roll a total of sum of 11 from all 4 rolls? All right. So we're looking for sum of 11. And a standard 8-sided die has sides 1 to 8. All right. Okay, first thing we want to check. We don't I guess maybe this shouldn't be the first thing, but you should check it anyway. So in we will have to like account for overcounting in stars and bars sometimes. We need to see if we can do that, if we have to do that here. Okay, so what's the worst case scenario? You have like a really big number and the other numbers are all ones. So if you have 3 1 rows, then the remaining number would be 8, but that's already in the range of the die anyway, so that confirms we don't have to exclude anything. So we're just really like solving the normal ways to have a plus b plus c plus d is equal to 11, where a, b, c, and d are all positive. And like as I reiterated with the stars and bars formula previously, this is just 11 minus 1, choose what? 4 minus 1, and that is equal to 10, choose 3. I'll just draw the binomial symbol again, although it's kind of a bit of a waste time. 10 choose 3, and that, if you work it out, is 10 times 72. It's 120, yeah. It goes 120. So that should be your final answer for this problem. Again, it's just straight up stars and bars. Although you could put a twist on it, you can put twists on it. Like let's say the die were like die 1 to 7 with a 7-sided regular die. Sided regular die. Okay, how did you do this? Well, at first glance, it's the same, except you need to exclude cases where stars and bars here counts stars and bars like around this step counts numbers that are counts like things with numbers that are bigger than 7. Okay, so how we take care of this is, well, let's say one of these numbers, take a, is bigger than 7. Suppose that's the case. Well, then we know a minus 7 is greater than 0. And we don't know much else about it, okay? And this is the same restriction we have on a normal stars and bars. So if we subtract 7 from a, let's say a prime is equal to a minus 7, then we have a prime plus b plus c plus d is equal to 11. Minus 7 is equal to 4. All right, now actually this fits the stars and bars form, so we apply stars and bars on this. And remember, this is like overcounting invalid cases that we want to exclude. So we have 4 minus 1, choose 4 minus 1, because it happens to be 4 variables and the sum happens to be 4 as well. And this just happens to be 1. Right. But another thing we have to account for is any one of the variables a, b, c, or d can be too big. So we multiply this count by 4 since it'll be the same for all variables. Okay. So yeah. 4 times 1 equal to 4. And then we can just subtract that from 120 to get an answer of, it should be 116. Unless I made like some dumb mistake, but I don't think I did. And if you think about it, this process is basically just the same as ruling out 8 plus 1 plus 1 plus 1 and its different orderings as solutions, whereas you didn't have to for the 8-sided die. So yeah, that's pretty much all I got. And yeah, I hope you had a good time and learned a lot from this class. All right, or learned at least something maybe.